Hello, I'm Raoul Reiser, and I am an associate professor in health and exercise science at Colorado State University. I'm also the director of the clinical biomechanics laboratory, and I'm going to be talking with you all today about hooves on surfaces. But before I get into that, I want to thank the NTRA for hosting this meeting and providing me the opportunity to speak with you. I'd also like to thank all the sponsors. I've been involved with organizing small meetings in the past, and I know how important these sponsors are to the overall success of these meetings. So I want to thank them for their support. And I also want to thank Mick Peterson for inviting me specifically to talk with you. I know that many of you may not recognize my name as being associated with horses and horse racing. You may recognize Colorado State as having a history with horses. And so I do want to provide you with a little bit of background as to where I fit into this puzzle. Well, basically about 25 years ago, Wayne McElraith, who you may recognize the name of, Wayne's been involved as a vet surgeon with race horses for multiple decades. And back in the late 90s, he got a conversation going with Mick and eventually brought me into that conversation as well. And Wayne was interested in trying to figure out the role that the racetrack would play potentially in the health and injury risk of the racehorses. At the time, didn't know much about how the track affected them, but oftentimes the track was blamed for racetrack breakdowns of horses. So if you know Wayne, Wayne can be very convincing, and he convinced us to give it a look. And we started by doing a lit review as you normally would, and we found a few things that we thought could help us out. One of those being a paper by R. McNeil Alexander from back in the mid 80s, where he examined a variety of different animals, including horses to a small extent, but also more compliant paw pads of animals such as kangaroos, and the role that that foot and the paw pad played in locomotion. And a very simple model, as you see on the left-hand side of the screen here, basically just the mass of the animal, a spring representing the stiffness of the leg, then you have the mass of the foot, stiffness of the foot, and then a damper in there that would be related to potentially dissipating some energy from the system. So we started with that, and we combined it with some very basic material property information that we were able to gather on some soil types, and basically added that into the model to add the mass of the soil, the stiffness of the soil, and some dampening properties of soil. And from that, we did see that you could dramatically change peak forces on the limb here in this max vertical GRF column. We see that we can go from about 2.1 to 2.5 times the weight of the animal, with some significant changes in the stiffness of the surface. Also, the loading rate could be changed quite a bit, energy dissipated, so forth. So basically, this paper published in 2000 sort of gave us some preliminary information to which we then went forward with to try to further understand the potential role of the racetrack. Mick has definitely taken that banner and ran with it. I've sort of been on his team the whole time and have helped out with many of the projects. But overall, being that I am in a health and exercise science department and having a clinical biomechanics lab, most of my work right now is related to humans, and specifically a lot of the same stuff that we're going to be talking about in just a minute related to horses, I work with on the human side of things. So if you come to Fort Collins and look me up and have a chance to visit my lab, you would see that the lab is basically covered in artificial turf right now. We've got force plates in the middle of that. We've got a camera system for tracking motion. We put little reflective markers on people, and we basically then distill things down to look at those ground reaction forces and then the loads at the knees and the ankles related to performance and injury risk. We also have high-speed camera capabilities to zoom in and really look at how that foot is interacting with the surface. So a lot of the stuff that I learned on horses, now apply it to humans, as well as continue to work with horses as well. Getting back to the racehorse, it is the front limb that we are the most interested in. And as we go to the second bullet here to start with, we see that even today, with the most recent data, and data is being captured way better now than it was 25 years ago on racetrack injuries, but the forelimb is still the most likely to fracture, and it will vary from the type of track that you're on. The forelimb fracture is highest on dirt tracks. Then the hindlimb fracture is more likely on a turf track than a dirt track, and then it is typically the left forelimb and the right hind limbs that are more likely to fracture on dirt. So it is important to realize that depending on the surface you're on, it will change things a little bit. And we are going to focus our time today talking about that forelimb, but do want you to know that we are currently also developing models to better understand the hind limb and hind limb fractures of racehorses. If we go back to the first bullet on this slide, we also see some information from another paper related to the fact that depending on the type of track you're on, it will alter the fatal injuries of the horses. So overall, we do have some evidence, epidemiological at least, that racetrack does play a role in the type of injuries that can happen, and they can vary, but it is that forelimb that is at most risk. And why is that? Well, first we're going to talk a little bit about the galloping horse. And the galloping horse has a lot going on in a very short period of time, as it's, for each of its stance phases. And typically, if we look at the upper right-hand image here, it begins with a flight phase. And then after that flight phase ends, is one of the hind limbs that makes first contact, and then the second of the hind limbs will make contact. And that second limb of the hind limb to make contact would be referred to as the lead hind limb. And then from there, you would have one of the forelimbs followed by the second of the forelimbs making contact. And then that second forelimb that makes contact is known as the lead forelimb. And that lead forelimb ends up being the last in the sequence to make contact, but it ends up bearing a huge burden as it then takes on the sole role in the ground reaction force paradigm and eventually prepares it for the next flight phase. Depending on whether or not the same hind limb that's in the lead is in the lead with the forelimb will depend on whether or not it's referred to as a transverse gallop or a rotary gallop. Rotary gallop has the hind limb and the forelimb that's leading being on opposite sides of the body, while the transverse gallop has them on the same side of the body. Either way, that lead forelimb, goes through basically the same loading through on this stance. One of the key things to realize as we look down to the bottom left here on the slide is that for the majority of the time that lead forelimb is on the ground, it's the only hoof that's on the ground. So it is taking on the vast burden of the ground reaction force while it's on there. Only about 1/100th of a second that it's on the ground is the other forelimb on the ground. Both the hind limbs are off the ground at this time. And in total, that limb isn't even on the ground for 1/10 of a second. Okay, about 0.08 seconds here from some data that Leach published back in the 1980s. So very short period of time, but a lot of forces being generated and having to be dealt with during that time. On the left-hand side here, here's some vertical ground reaction force data from Ratzlaff back in the 80s. And he was one of the first people to actually instrument all four hooves of the horse to get a sense of the magnitudes of the forces on the limbs. And this is sort of a staggered set of tracings where it begins with the left rear, then the right rear, then the left front, and then the right front. So this would be a right front lead. And you can see the progression of the limbs on the ground in time, how there's very little overlap with the left front to the right front here. And majority of the time then that lead limb is the only one on the ground. And if you look at the comparisons of the magnitudes of the forces, you only had a load cell measuring a small portion of it, so you don't want to think that there's only 80 pounds on the limb. It's just a small subset of the total force on the limb. But if you were to compare the different peak values here, that forelimb has about forces that are about 20% higher than any of the other three limbs. So definitely the largest burden in terms of a small amount of time and very large forces. Those forces do equate out to being about 2.5 times the actual weight of the animal. We don't have any of the forces here scaled specifically to that. We have newtons per kilogram here, which you can eventually backtrack out to that. But that peak force can be about 2.5 times the actual weight of the animal mid-stance of that ground reaction force profile. So very significantly large forces, very short period of time, and basically three main things going on during the course of that stance phase. We can talk about an impact at the initial contact, then the support phase, and then what we call the breakover at the end. The impact is mainly associated with that hoof making contact and securing its grip or stance on the ground. Then once that happens, then there's a high rate of loading to that peak force where we're supporting the weight and the acceleration of the center mass of the horse. Then eventually, as we work our way towards push off or breakover at the end. So yes, the vertical forces are the highest of the forces, but we also need to make sure that we realize that the horizontal force is also very important. Again, there's going to be this impact phase, which is a little bit irregular, kind of like we see it on that vertical side, a little bit irregular there as that hoof is digging into the turf and gaining its purchase on the ground. But it's negative here, meaning that it's actually a braking force, actually slowing the horse down a little bit because that limb is out in front of the horse. And so it's slowing things down a little bit. And then during the second half of stance, you have to speed yourself back up or go into that more propulsion phase. So we have a coordinated sequencing of both vertical and horizontal forces that we need to be conscious of as we think about the loading on the limbs. Here in this next image, we can see a little bit better of that actual orientation of the limb during the course of these forces. Also on here, we have the resultant of the vertical and the horizontal, so we can see the orientation of the total or the magnitude of the force. And for that magnitude of that force to be safest for the animal from a bone fracture perspective, you want that force to be directed along the line of the bones. If it's offset from the line of the bones, it's going to put a greater torque on the bones and potentially put it at a greater risk of a bending type fracture. So making sure that the limb is oriented properly with the center mass of the horse is very, very important. Also, we see that, again, we can see that there's this braking component early on and more of a propulsive component towards the end, and then that purely supportive, almost vertical force mid stance there. Also, we can see that when that limb is coming in, it doesn't necessarily impact purely flat to the ground. It's coming in usually a little bit heel first, and so there is some rotation of the hoof going on when it's first making contact, which can also play a role in that variability of these forces at initial impact. And then at breakover, we also have some rotation of the hoof right there as it goes more toe off at the end of the stance phase in propulsion. The other thing that we see on these bottom plots is a dotted set of arrows. These are related to the acceleration of the hoof. So early on, when that hoof is coming in and gaining purchase on the ground, it's highly accelerating. And so that actually is, well, what's mainly responsible for those early on forces is the deceleration in both the vertical and the horizontal direction of that hoof. Then once that hoof, sort of gets down to zero velocity with the ground, not accelerating anymore, then it's more of the supporting of the center mass or the mass of the rest of the animal. And so we talked a little bit about the fracture risk there early on. Later on, when we have the suspensory apparatus fully loaded mid-stance on through breakover, that's when we would be putting our horse at greater risk of soft tissue injuries. So depending on where we are in the stance phase, may have more of a risk for bone or soft tissue injuries. As you might imagine, the faster the horse runs, the greater those forces are going to have to be, because the hoof is going to be on the ground for an even shorter period of time. It's going to have to do more with that shorter period of time while it's on the ground. We also would have larger forces if it's a heavier animal, of course, and then also potential for changes in the forces based on fatigue as the horse is racing around the track. And when we think about fatigue, we don't want to think about just instantaneous acute fatigue that may be building up during the course of the race, but you also can think about fatigue as being something that has accumulated from prior training and could be ever present from day to day. And it has been shown that fatigue can actually increase the loading on that lead forelimb. Because what they found is that a fatigued horse will tend to try to spring up into the air a little bit more. So basically have a greater flight phase. And we saw that when you come back down, then you have to decelerate that downward velocity of the center of mass. And so that could potentially increase the peak vertical forces and then the loading rates needed to get to that peak force in that short period of time. And then we also have noticed that with the fatigue, there tends to be what's referred to as overstriding, where the lead limb is stuck further out in front as it's trying to eventually make contact. And that can also then increase those horizontal loads, i.e. braking forces, because that limb's further out in front, and then it has to catch up with more propulsion later on. So we also have a fatigued horse probably at greater forelimb injury risk, whether it's acute fatigue or chronic fatigue that may be existing even prior to the race. Another important piece to be mindful of is the fact that the horses always aren't just thinking about making forces that are in that forward, backward direction and that vertical direction. Whenever there is a turn, while the instantaneous velocity as you go around a turn is tangent to the path and forward, in order to change that velocity so that it redirects and keeps you on that path, you have to have a centripetal acceleration towards the center of the circle. Well, from Newton's second law, F equals ma, in order to have that acceleration towards the center of the circle, we have to generate some forces to accelerate it in that direction. Those forces coming from additional ground reaction forces. So if we go to the bottom diagram here, to the ground level, we see that we need to have a medially directed ground reaction force now to go along with any vertical and forward backward ground reaction forces. So in this diagram here, the center of the circle would be off to the left here, and we need to have a force to accelerate ourselves towards the center of that. Well, easiest way to try to generate that horizontal force is to lean in a little bit. Leaning in allows that vertical force that you had before to now be directed a little bit more laterally inward, so it helps it to readily make that force. But we also have to be careful that when leaning, that we don't change what each of the limbs is responsible for and the loading to too great of an extent, because as you lean in, you would typically put a greater support burden on the inside limb and then that greater lateral force production on the outside limb. And that's the role then that the banking oftentimes can help us out with. If we put a bank onto the track, that can help reduce the asymmetries of the horse from leaning in and make those loads just a little bit more symmetrical. Won't completely solve the problem, but helps out quite a bit. Also, one of the things when we think about going on a turn and wanting to lean into that turn, it's also necessary to do that to prevent toppling. Toppling, term in reference here to falling to the outside of the curve. You know, that's the natural thing when you run around a curve. You know, if you don't lean in, you basically are leaning out. You're feeling like you're going to be thrown out or topple, fall over. And that's because of a torque that is produced by that horizontal ground reaction force, that if you don't counteract that torque, you'll actually fall. And that torque actually is to have you rotate outside the curve. So by leaning in, your weight can help to offset the torque being generated by the ground reaction force. So leaning is a very important piece of the puzzle, does induce some asymmetries, but hopefully with proper banking, we can also help alleviate some of those issues. One of the things that the jockey and the horse do in order to help make those turns a little bit better is to go into a left lead. Well, that is going to put a greater burden on that left limb during the turns. And so when they come out of the turn, typically we'll then switch to a right lead coming out of it to help change the stressors on that limb. So a horse will typically change lead multiple times throughout the race. Now that we've talked a little bit about the basics of the ground reaction force and the needs of the horse as it's galloping, we want to talk about that symbiotic relationship that that horse needs to have with the surface. It's not going to be able to create those forces if the surface doesn't interact properly with it. And as we said early on, surface from the epidemiological data does seem to have some influence on injuries. We also know that when we talk to the jockeys, they can very quickly tell how a surface is behaving in certain aspects from day to day, both in terms of how the horse responds to that surface, as well as the feel that they're getting from that surface as they're being carried around the track by the horse. And through that, there are discussions of it being a fast track or a slow track. You can also hear about different components of the track, such as firmness, cushioning, responsiveness, and grip as some of the four of the most common terms. I don't want to get into the details of what each one of these terms means, but what we're getting at here is that there's a lot going on with that surface that can potentially change the way that the horse interacts with it, and then the loads and potentially risk of injury as well as performance-related characteristics of it. What I want to do is kind of go beyond these sort of more common terms to get into some of the terms that we hear about more on the materials properties side of things. When we talk about soils and grass type surfaces, we tend to hear about them being highly deformable, and a lot of that deformation is permanent, meaning that the track will have to be groomed again, or the grass will have to be given time to regrow. So not only deformable, potentially permanently deformable, it needs maintenance. Anisotropic, meaning that the properties are different depending on the direction that it's loaded in. Nonlinear, so not your classic spring that has linear properties, but more of a nonlinear piece to it, where the faster you load it, the stiffer it might be. And that also gets into the strain rate dependence here. And then viscoelastic, from the notion that water plays a huge role in the way that the material will respond to loading. Elastic, meaning that it is deformable. Some of that deformation will return, but as we said, some of that deformation may be permanent. So, and then we also have knowledge that the shear and the normal or vertical responses are highly coupled. They're not independent from each other. What all this means is that if we are going to be testing the track to get an understanding of how the track may be playing a role beyond just getting anecdotal evidence from the jockeys, is that we actually have to test the track in a manner that loads it similar to the way that that galloping horse loads it. So that gets us back to the modified R. McNeil Alexander spring mass dash pop model that we brought up early on. We can actually do a pretty good job of mimicking the loading of the horse through that simple setup of springs, dash pots, and masses. Basically, what we need is a mass representing the whole mass of the horse, a mass representing the mass of the hoof, a spring and dash pot for the limb, and then a spring and dash pot for the hoof. And then if we have that set up in a testing device, we can then load the surface consistently from day to day, minute to minute. Also, talked about the need for not only vertical forces, but also horizontal forces. And so we have to think about basically taking the spring mass dash pot system and slightly rotating it so that we can get horizontal and vertically on the horse. And so that's the direction that we took with the development of the OBST, which has become one of the standard track testing devices to get not only vertical information, but horizontal loading information not only about the initial impact of the hoof, but also the support phase later on. And so if we dissect into some of the earlier pictures of the OBST from when it was first published back in 2008, we do see that we have a device that has basically two masses to it, one for the hoof and one representing the mass of the horse. We don't actually have to have the mass of the horse, the actual mass of the horse. The actual key thing is to match the energy that the horse puts into the material. So we can adjust that energy through not only adjusting the mass of the main system, but also then the velocity that it impacts with. And so we don't actually have to, carry around weights that are the same as a horse, but yeah, we can get a good representation thereof. And you can see that there is a lean, backward lean, 12 degrees here, and then 7 degrees at the hoof to help mimic the fact that the hoof doesn't coming in at the same velocity that the center mass comes with. And then we have springs and dash pots in there to represent those components of the limb and the hoof. So the system designed to mimic the biomechanics, ground reaction forces of the hoof and do it repeatedly. It's one of the things that is probably the most important that we've learned early on by using the OBST is how important it is to have consistency around the racetrack. And that's important for the horse. The horse needs to be able to know that if it's going to go out there full effort, full gallop, maximum velocity to win the race, it has to trust the surface. It has to know that that next step, that ground that it encounters, is going to be the same as the last step. Okay, and so that's one of the things that we can do with the OBST when it's hooked up to a vehicle or on wheels and moved around, is that we can test the whole track, not only near the rails, but further away from the rails. Make sure that there is a consistent base underneath and the rest of the surface is being cared for properly. So that's number one, making sure that we have consistency, i.e. uniformity in the track. And then the next is to build upon that to learn how moisture and organic matter or synthetic carpet fibers or waxes, you name it, all those different components can potentially play a role in the loading of the limb that the horse may encounter as it gallops. And I'm not going to be going into the details of any of those things. Those will follow in some of the talks that are later on in the conference. So with that, I'd like to go ahead and close and say thank you again for allowing me to present this material to you. If you do find yourself in Fort Collins and want to talk or see my lab, definitely feel free to give me a shout. Or if you have any questions about this talk, also show you real quickly the bibliography so that you have that in regards to the sources that I referenced in here. And then a couple seconds for this second page of references here as well. Again, thank you.